All right, so our goals today are primarily to talk about, start talking about proofs and different ways to do proofs using propositional logic. This should give you everything you need for the next homework and also for the quiz which is coming up. So administrative details first, and then I'll ask for questions. There's no school on Friday, okay? Friday the 11th is listed as a faculty work day. So the faculty have to come in and do work for a change, and there's no classes on Clark. So we won't have class on Friday, which means the homework that was supposed to be due on Friday, I moved to the following Monday. But we don't meet on Friday to talk about homework, so pretend it's due on Friday and ask questions by Wednesday's class, okay, if possible. And then you got the weekend to write it up. I've also canceled class for November 1st. So November 1st, I'm going to be up north at a statewide computer science meeting. So I'm canceling all my classes for that day. That's a Friday. That was the original date for the midterm for this course, so I moved the midterm back to the Wednesday right before that. So I think that's the 30th of October. And that's updated on Canvas, and you should have gotten an email this weekend when I changed it. And then Wednesday will be an in-class quiz. I'm going to give you 45 minutes for the quiz. You can use 4 pages of notes.
This coming Wednesday?
This coming Wednesday, yeah, so 2 days from now, and that should be kind of like a homework set, but we'll talk about details of that in a little bit. So any questions before we start talking about, I want to go over the homework that you just got back, and then I want to start talking about proofs. So the homework came from a few sections. 1.5, which was on summations and products and stuff, we talked about that last week when you turned in your homework. Let me talk about some of the stuff from section 3. In particular, question 1. So this is like something that you're going to see on the quiz on Wednesday. So look at question 2, for example. It says, for each of the following propositions, identify simple propositions, express the compound proposition, that's the statement, in symbolic form and determine whether it's true or false. So let's look at A. The world is flat or 0 is an even integer. Is that a proposition? Right? It's a declarative statement. It has a truth value.
Yes.
It says the world is flat or 0 is an even integer. But it's a complex proposition that actually contains smaller, simpler propositions put together in some sort of logical way. So we could break that up into smaller propositions. For example, I could say, let W be the proposition, thank you, which says the world is flat. And let Z be the proposition 0 is an integer. Be the proposition 0 is an even integer. So I've defined 2 propositions. W is the proposition the world is flat. Z is the proposition 0 is an even integer. And so this original proposition says the world is flat or 0 is an even integer. So in terms of these 2 propositions that I've written, I could write W or Z. And this means the same thing as the original statement, right? So this is just taking a sentence and breaking it down into smaller propositions combined using the rules of propositional logic. And we're doing this because typically we'll be doing word problems, we'll be asked to show something or conclude something, and it'll start with statements like this. And if you're given a big statement like that, there's really nothing you can do until you break it down into smaller pieces, right? So typically these statements will have something to do with each other, and we'll put them together into a proof, and we'll do an example of that shortly. So the goal in this question, which was one of the questions I looked at, was to identify simpler propositions. So for C, 5 is a prime number, that could be a proposition. 6 is not divisible by 4, that's another proposition. And C basically says whatever that first proposition is, and, right, a caret, second proposition. And each of these are, the first one is an or, the last three are ands. The second one is an implication. If 432,802 is a multiple of 4, then 432,802 is even. So the propositions we might write there, (802) is a multiple of 4. So let P be the proposition that this thing is a multiple of 4, and let Q be the proposition 432,802 is, it's supposed to be even, is even. And so that compound statement is simply just an implication, if P then Q. If this thing is a multiple of 4, then this thing is even. But once we have statements that were written in English in the form of this or that, we can start to use identities and logical equivalences and things like that to transform our statements from one thing to another until eventually we've hopefully shown whatever we're being asked to show. So that's going to be the basic strategy. So that was the point of question 2, was just to get some practice doing those kinds of things. And then determine whether it is true or false. So the world is flat or 0 is an even integer. Well, that's true because the second statement is true. And if one piece of an or is true, then the whole thing is true. If this thing is a multiple of 4, then this thing is even. Is that true or false? Question 2b.
True.
Why is that true? It is true.
The only time it would be false is if the hypothesis was true and the conclusion was false.
Okay, so P and Q, P is called the hypothesis, Q is called the conclusion. And if you look at the truth table for if P then Q, it's almost always true. The only time it's true is exactly that case. If the hypothesis is true but the conclusion is false, then this if-then fails to be true. So what's the truth value of P? Is 432,802 a multiple of 4? No, so this is false. Is 432,802 even? Yes. Well, if the hypothesis is false, it doesn't really matter what the conclusion is. The implication is considered to be true. So P arrow true, P arrow Q, that is true. And it's a little weird because the first part of the if-then is not true, right? This thing is not a multiple of 4, but the if-then is actually true. 5 is a prime number and 6 is not divisible by 4. Yeah, both of those are true, so that compound proposition is true, and so on. D is true, E is false because 2/3 is not an element of Z, it's not an integer.
Nick, can you talk again why you had an objection? You kind of want us to write let W be the proposition of, instead of just saying W equals. What was your objection to saying W?
Because when we get to a proposition like n plus 1 squared equals n squared plus 2n plus 1, this equal means something fundamentally different from this equal, right? What we really mean is P is the proposition that this is equal to that.
I got you.
And it's just too easy when people are doing this to start using this as a synonym for P, and it's not a proposition, and then it starts getting into trouble.
I got you.
So P is the proposition. Okay, so here comes the good stuff. Let's talk about rules of inference. And I feel like it's heating up in here. It was like a comfortable 72 this morning. It's pushing 77 now. All right, rules of inference. So this is ways that we can draw conclusions from other statements. So let's put down some propositions. If I win the lottery, then I'll buy a new hat. So I'm telling you that this is a true statement. Okay, it's a proposition, and I'm saying this is a true statement. I'm going to give you another true statement, which is I win the lottery. Should say I won, but I win. I won the lottery. I did get a winning lottery ticket though for $5 about 2 years ago, so I'm on my way. Okay, if I win the lottery, then I'll buy a new hat. That's the first statement. That's true. Second statement that's true. I win the lottery. Can we conclude anything from these two statements taken together? What can we conclude? I'm going to buy a new hat. We don't actually know if that first statement is true. Okay, that may or may not be true. We don't actually know if I've won the lottery or not. You can't read my brain, you can't predict the future. I might win the lottery and I might lose my mind before I get to buy a new hat, right? And nobody can predict if I'm going to win the lottery as far as I know. But here's something that we can say. If that first statement is true and that second statement is true, I can guarantee that third statement is true also. So let's do this. Let P be the proposition I win the lottery. Let Q be the proposition I'll buy a new hat. So that first statement says if P then Q. Might be true, might not be true. That second statement says P. Might be true, might not be true. But what we can say without doubt is if this first statement is true and the second statement is true, then this third statement Q is true. Okay, that's the nature of what we can do with these rules of inference. So let me number these statements. 1, 2, 3. So what this says here is if 1 is true and 2 is true, then 3 is true. And this is the proof, or it will be when we add a few things. So when we write a proof, we're going to have the following things. We're only going to write down things that we are either assuming are true or that are true because of the things we've already written down. Okay? If this is an assumption, we're going to say we're assuming this is true. If it's something we're given, we're going to say this is something we've been given is true. If this is something that follows from previous statements, we're going to list a reason why it follows from those previous statements. And so everything we write in this proof is going to be true. And when we draw this horizontal line, that basically means therefore or then. Given the truth of all the things above this line, this thing below the line is also true. And in the book and in the homework questions and on the quiz, you'll see this written differently. You'll see something like this: P arrow Q, comma P, double arrow Q. And when you see this notation, what you should think is this first part is something that we're given is true, and the second part is something that we're given is true, and this arrow is like the vertical line, and the Q is the thing that we conclude from everything that came before. So this is not if P then Q. Okay, this statement is saying, let me write it again without the circles. This statement is saying, given this and given this, we can conclude that. Okay, the double arrow is really that horizontal line, which says, given the truth of everything to the left, we can conclude the thing to the right. It's just a more convenient notation to typeset than writing things vertically. We could also write this a different way. We could say, given P arrow Q and given P, if all of that is true, then Q is true. That's too many arrows in parentheses, so we don't usually write it like that. But this is definitely a true statement. If this is true and that is true, then all of that implies that Q is true. And so if you look in your text around page 58, you'll see a list of rules of inference. So common implications and equivalence. So this first statement we've been working with is called detachment. Okay, it's also called modus ponens, but we can call it detachment. If P then Q, and if P is true, then Q is true. We sometimes call this direct reasoning also. So this is detachment, or direct reasoning. So that's a rule of inference. Here's a slightly different form. Suppose we know if P then Q is true, and we also know that Q is false, not Q is true. We can conclude not P is true, or in other words, we can conclude P is false. So if I win the lottery, then I will buy a new hat. I did not buy a new hat. What can we conclude? I did not win the lottery. And that's got to be the case, because if I won the lottery, then Q would have been true, and Q was not true. So P can't be true. So this is indirect reasoning. Disjunctive addition. Given P, we can conclude P or Q. If I win the lottery, then I win the lottery or I buy a new hat. Q could be anything. Doesn't matter what Q is. If I win the lottery, then I win the lottery or 1 + 1 = 17. This statement that we're concluding simply says one of these has to be true, and if P is true, then one of these is true. All right, so we're just adding something into this, and the result is still true. Conjunctive simplification. If we know that P and Q are true, then we know that P is true. Why? Because for the AND to be true, both P and Q have to be true. So similarly, given P and Q, we can conclude Q. So here's a grand one. Given that P implies Q and given that Q implies R, we can conclude that P implies R. That's a chain rule. If I win the lottery, then I'll buy a new hat. If I buy a new hat, then I'll get my picture taken. So if I win the lottery, I'm going to get my picture taken. And it just comes from putting them together. And we can extend this out. It could be 25 things. A implies B, B implies C, C implies D, Y implies Z. And then if we're given A, we can conclude Z. And so I'm not going to write all of these out, but they're in this table, page 59, I believe. So that's a chain rule. Conditional equivalence. If P, then Q is the same thing as not P or Q. That just comes from the truth table. Biconditional equivalence, don't worry about. Contrapositive, we've talked about a little bit, but let me write that one out. If we're told P implies Q, then we know that not Q implies not P. And that's kind of like indirect reasoning. If I win the lottery, I'll buy a new hat. If I don't buy a new hat, then I did not win the lottery. We can conclude this from the previous.
You can ask a question. On page 55, it gives us a hierarchy for interpreting propositions.
Yeah.
And you go negation, conjunction, disjunction.
Okay.
Can you?
I'm going to say use parentheses.
Well, that's what I see. Like I'm saying, for an example, like a problem on page 90, and that's chapter 3. Is that where it's?
I don't know if my page 90 will be the same, but.
Well, but it's problem 13. It says not Q, single arrow, not P. And I'm just picking that out as an example. That's the right-hand side. What's to prevent me from interpreting that as not squiggle the everything else that comes after that?
So
It seems to me like there's some ambiguity.
Yeah, so negations are usually highest priority. But beyond that, right, so if you wanted to be completely unambiguous, you could write this. But that's just going to look like Lisp or something with lots of parentheses. So, so when you have not a variable, that's an atomic thing,
Okay.
right? But in general, use parentheses if there's ambiguity possible, right? Certainly if you meant not P implies Q, you definitely want to write it like that. But if you mean not P implies Q, I'm going to interpret that as saying not P implies Q.
Okay. And then.
But I don't want to rely on priority between those and so on. So.
Okay, so then how do you fit? You've got on page 55, you've got first negation, then conjunction, then third disjunction. How do you fit the implication symbol, the double arrow, in there?
From context. So use parentheses because I can see ambiguities.
Yeah, I can too.
I mean, usually we would be talking about this implies that, and if we meant P and Q implies R, or S, we would put parentheses there, but
Is it just really not going to come up with problems?
I don't think it's going to come up. If you're unsure, ask, right, definitely. But I'm going to say that negation is highest priority, and implication is next.
Okay.
If you want priorities, and beyond that, use parentheses. And I usually don't try to deliberately trip people up. So if it looks ambiguous, it's probably an oversight on my part, and definitely come up and ask. All right, so why do we care about all of these rules with crazy sounding names? Because we can use them to solve problems. So let me give you a sample problem. And this will be a word problem, but then we can use this for things that are already in the form of symbolic logic. So here's an interesting problem. If you send me an email, then I'll do my homework. If you send me an email, then I'll do my homework. If you don't send me an email, then I'll go to sleep early. If I go to sleep early, then I'll wake up refreshed. Therefore, and we can write 3 dots to mean therefore, if I don't do my homework, then I'll wake up refreshed. So that's a weird set of statements. If you send me an email, I'll do my homework. If you don't send me an email, I'll go to sleep early. If I go to sleep early, I'll wake up refreshed. Therefore, if I don't do my homework, I'll wake up refreshed. And that might or might not seem to make sense to us, but we can prove whether or not this final statement follows from the previous statements. And we don't know if those first 3 statements will be true or false, but we can say if those first 3 statements are truthful, does this 4th statement necessarily follow? So what do? First thing we do, we switch this into the language of propositional logic. So we need to make some propositions. Let E be the proposition. You send me an email. Let H be the proposition. I'll do my homework. What else do we need? Don't send me an email is going to be simply not E, so we don't need a new variable for that. I'll go to sleep early. Let's make a proposition S. Let S be the proposition. I'll go to sleep early. And go to sleep early, that's S. I'll wake up refreshed. Let's make a proposition R. Let R be the proposition. I'll wake up refreshed. So that's enough propositional variables for us to rewrite these 4 statements in the language of propositional logic. So using these symbols, what does this first statement say? If you send me an email, then I'll do my homework. How can we write that? Yeah, that's just E, arrow, H. And I'm going to label that. And why do we know that's true? Well, we don't. But we're going to just say this was given to us. Because our goal is given this and this and this, can we prove this 4th thing? So statement 1 is given to us. Okay, what about the second statement? If you don't send me an email, I'll go to sleep early. What does that look like? If not E, then S. And that's also given. Sometimes these are called a premise. Something we're presuming. Okay, what's the third statement, which is also given to us? If I go to sleep early, then I'll wake up refreshed. Now, what we're trying to show is this 4th statement. I can't write this down as part of my proof. If I write this down here, my proof is invalid because that doesn't follow from anything that we've already written. But I can cheat. I can put a little area over here. I'm going to say ignore. And if you do that, if you make an area called ignore and you mark it off with a line, then I won't consider that to be part of your proof. And you can write in there, the continuum hypothesis is true, and you won't lose points for it. Okay, this is your scratch area. And what I want to use my scratch area for is to write down what I'm trying to get to. I'm trying to show this. So I want to show, if I don't do my homework, then I'll wake up refreshed. So what does that look like? Not H implies R. That's where I'm heading. But it's not part of my proof yet. Okay, so I don't need my original statements anymore. I've got these nice clean expressions to work with. What can I possibly do that's going to get me to R? I feel like I missed something. No, we're good. Okay. So we want to use these rules of inference, direct reasoning, indirect reasoning, contrapositive, and somehow show not H gets us to R. So any ideas what we could do?
We can use contrapositive reasoning for the first one.
Okay, we can use contrapositive reasoning for the first one.
So it'd be not H, then not E.
If not H, then not E. And we have to give a reason, and the reason for that is contrapositive applied to rule 1. Now anybody looking at this proof, the first 3 arguments are given, they can't disagree with those. The 4th one they can say contrapositive. That says P implies Q is equivalent to not Q implies not P. Applied to statement 1. 1 says if E then H, so contrapositive says not H then not E. Yeah, that's valid. That definitely follows. And maybe that will help us, maybe not. This is a game, it's a puzzle, right? You have a set of things you can do, and you're trying to somehow take what you've got and turn it into this. It's a trial and error thing. Sometimes you can see immediately why this is true, and then you can try to figure out what are the logical steps I can put down. Sometimes you just do random stuff until you stumble across the answer. So this feels like a good step. What can we do after this? Okay, let's do the chain rule on 2 and 3. This says not E implies S. This says S implies R. We can put those together and say not E implies R. That's the chain rule. 2 and 3.
Can we chain the chain rule?
We can chain the chain rule. What do you want to chain?
I just put all 3 of them together. Not H implies not E, arrow S, and S.
Okay, so yeah, for starters, I would do it in just the straight chain rule. Just chain 2 things at once. But we can effectively do a big chain rule, because now we know not H gets you to E, and E gets you to R. And so not H gets you to R. And that's one more chain rule. And that's 4 chained together with 5. And what have we done? We've proven not H implies R. Which, if we go back to our original definitions of our propositions, will say, if I don't do my homework, then I wake up refreshed. And we can say, which is what we were asked to demonstrate. That's the end of your proof.
Can we chain more than 2 things?
Ultimately you can, but for starters I would do 2 things at a time. If you have to chain like 26 things, that's a pain. But it's clearer to do 2 at a time. Alright, so there's a 6-step proof that in fact if I don't do my homework I'll wake up refreshed, given those first 3 statements. Alright, is this making sense? So those are rules of inference. Let me show you the flip side. The flip side has what we call fallacies. So here's the 2 common fallacies we want to know. Given if P then Q, and given Q, we try to conclude P. And that is not logically correct. This is called the fallacy of affirming the conclusion. If I win the lottery, then I will buy a new hat. I buy a new hat, therefore I won the lottery. I might just go out and buy a hat even if I didn't win the lottery. Right? So given the conclusion being true, we cannot conclude that the hypothesis must be true. The implication only goes in one direction. If P, then Q. If Q is true, P might be true, it might be false. Right? If I win the lottery, the sun will rise tomorrow. Well, it's probably going to rise tomorrow even if I don't win the lottery. So that's a common fallacy. Here's another one. If P, then Q. Not P, therefore not Q. And we can use the same example. If I win the lottery, I'll buy a new hat. I did not win the lottery, therefore I do not buy a new hat. Well, I could buy a new hat anyway. So this is the fallacy of denying the hypothesis. So those are not logically sound. And sometimes you're asked to identify whether something is true or to identify the fallacy that's being made. Alright, does that make sense? Grab a 5-minute break, and then let's start doing some more proofs.